Alright everyone, welcome back. So the question that a lot of people had after watching the last video was, okay, cool, you can rotate around the x-axis, maybe the y-axis. But what about a different line? And the answer to that is, of course you can. So let's look at what this will look like. So here we have some f of x and some g of x and blue and then in brown here. We're going to try and come up with an equation. So let's see what's going on here. So we take this area and we rotate it around in a circle around that axis. Okay, and here it looks like the line's like about y equals -2.5 or something. So what I'm hoping you guys will notice is this makes a similar shape, right? We still have a bunch of donuts that we're adding together. So we're still going to be integrating like a pi r squared minus pi r squared. It's just those radii are going to be different. Now, one thing worth noting is that when the axis changes, the volume changes as well. So if you move this volume, say down, or the axis of revolution down here, and then you rotate around, you're going to recognize it makes a much larger volume. So the line you rotate around actually does make a little bit of a difference in that. Okay, so let's go ahead and get to the math and let's take a quick look at that. Okay, so let's get a look at this example. Say we have the area between y equals 6 plus sine x, y equals 3, x equals 0, and x equals 2. So, and you're going to rotate this around the line y equals 1. Okay, so here's what your graph looks like. 6 plus sine of x, of course, looks like a sine graph that went up 6. So that's y equals 6 plus sine of x. And then let's go ahead and go from here and say, all right, well, what about the lower function y equals 3? So that's down here. And between x equals 0 and x equals 2. So that's going to go to 0 and then go to 2. So this is the region we're talking about. Now we're saying in this first example, we're going to rotate this around the line y equals 1. So let's sketch what that's going to look like. So y equals 1 looks like this. Okay, now as we saw from the video, this is my axis, as we saw from the video, we're still going to have donuts. So my volume is still going to be pi times some outer radius squared minus pi times some inner radius squared. Okay, now when we take a look at this, of course this will be in terms of x. When we take a look at this, hopefully we can see pretty clearly, like the outer radius is coming from 6 plus sine x. It's furthest away from the line we're rotating around. But it's not the height of the function. It's 6 plus sine of x minus 1. So the length of that purple line there, that purple radius, you should think about that as like a top minus bottom. It's a top minus bottom. So it's like 6 plus sine of x minus 1. So that's my outer radius. 6 plus sine of x minus 1. As for my inner radius is coming from the line y equals 3. And you should think about a distance between two functions as being a top minus a bottom. So the distance from 3 down to 1, that inner radius right there, is 3 minus 1. So that's a 3 minus, of course you could write that as 2. Okay. So that's how we set up our volume. So we still had like the function, we just had now the function minus 1. We still had the function, we just subtracted 1 because we were rotating around 1. And that was that top minus bottom distance. My bounds here pretty clearly are 0 to 2. So let's go ahead and plug that in our calculator. All right. So these are going to be a little ugly because everything is squared inside the integral. So let's go ahead and model what this will look like. So we're going to do second pi, and then I'm just going to multiply by the integral. So I'm going to integrate, let's see, 6 plus sine of x minus 1. Maybe you want to change the 6 and the 1 to be a 5 squared. And then minus 3 minus 1 is just 2, so 2 squared. And we're going to integrate all those from 0, 0, 2. So again, what that's doing is that's adding together all of these donuts that you get from like the inner rotation, the outer rotation, and just integrating those up from 0 over to 2. Okay, so when I did that on my calculator, I got 180.17244. Okay, so that's how we'll do this problem. Now, let's go to another example here. And we'll talk about the setup on this. So let's suppose now we want to do the same area, but rotated around y equals -2. And we're going to use this to come up with our key formulas for this lesson. Okay, so when we take a look at this, again, we have 6 plus sine of x, which is up here. And we have the line at y equals 3. Okay, and we're taking this area in here, and we're going to rotate that area around y equals -2. Okay, so where's y equals -2? Again, let's draw this in blue. So y equals -2 is actually down here. So there's the line y equals -2. So now when we think about what our radii are, they've actually gotten longer, right? If we try to measure like the distance from 6 plus sine of x down to y equals -2, that top minus bottom, that outer radius, and again, that's going to give a massive outer radius. And then we have a little inner radius. But that outer radius there, that top minus bottom, is going to be 6 plus sine of x minus the -2. So when I go ahead and set this up, my volume, again, is going to be pi times my outer radius squared minus my inner radius squared. It all comes back to those cross sections. We're integrating and adding together all those donuts across. And that's, again, that's what we're doing in the picture, right? We're adding, as we move this line, we're just trying to add together all these donuts along the way. And the donuts are bigger as the line got further away. But we're still just adding together all these donuts or discs to help us find the overall volume. Okay. So let's go ahead and work that out, what that's going to be. So my outer radius is going to be pi times, so integral still 0 to 2, we haven't changed that. So the outer one there is 6 plus sine of x minus a -2, so plus 2 if you want, squared. My inner radius is coming from y equals 3. So that distance right there from 3 down to -2. If I do 3 minus -2, it's always 5, of course. The inner radius is the same across there. So that's -3 minus a -2 squared. And then, of course, you'll plug this in your calculator. Okay, and I'm not going to do that for now. I trust you can plug things in your calculator. The setup is the important part. We have our outer radius. We're going around y equals -2. And I just subtracted, because I did like a top minus bottom, to help me find that radius in the inner, I subtracted the -2. Okay, now, hopefully you're recognizing the pattern. Here are the formulas. If you're going around the x-axis, or not around the x-axis, if you're going around a line of the form y equals k, your volume is pi times integral a to b of the first function minus k squared, and then g of x minus k squared. Okay, and again, this is your outer function, this is your inner. And outer, of course, just means furthest from the axis. Okay, so this is another one of those key equations. I want you to put a box around and kind of recognize what's going on there. All right, so let's look at one more example here where we have the line above the area. So let's say the area between y equals x and y equals x squared is rotated around the line y equals 3. So graphically, what's going on here is this is saying, okay, you have y equals x, you have y equals x cubed. We're rotating it around the line y equals 3, but y equals 3 is actually above that. So this is the line y equals 3. So our region is in here, but this region is being rotated around the blue line. Okay, so it's being rotated and going around in a circle like that. Okay, so I'm going to show you two different ways that you can kind of set this up. So we want to find, and of course the problem would ask us to find the volume. If you want to find the volume, you could say volume is pi times, okay. And for your outer radius, we could just use this function, right? So again, outer means furthest from the axis of rotation. So the way I do that is I say, okay, I'm going to do this in red here. I just draw a line from the axis into the area. And whichever one I meet first is the inner. So first I'm at the line. So the line, the y equals x, that's the inner. And the outer is the one that's furthest away from the blue line. So my outer one here is actually the parabola. That's why we don't do top minus bottom. We think outer minus inner. The outer one's coming from the x squared. So that's x squared minus 3 squared. I'm just using this formula right here. I'm rotating around y equals 3. And then for my inner radius, my inner is the one that is closer to that blue line. Closer to the blue line is just the line there, so that's x minus 3 squared. Okay. And then as for the bounds here, well, the bounds, we're going to have to set these equal. So I'm going to set x squared equal to x. So I'll get everything to one side, and then I'm going to factor out an x minus 1. So I'm going to get x equals 0 and 1. Okay, so yeah, that makes sense. I'm going from 0 to 1 there. And that's how we'll do this. So this is a way to do this. Now, another way you could do this problem. This is perfectly valid. This will give you the correct answer. Another way you could do this is you could think of the radius, again, itself, as top minus bottom. You still have to have the same inner and the same outer. But if you wanted to like measure this radius here, it's like, okay, how far do we go from y equals 3 down to y equals x? That purple distance right there is 3 minus x. It's top minus bottom. So you could also write that. Oh my god, I screwed this up. No, we're good. We're good. Okay. I could also write this as pi integral 0 to 1, 3 minus x squared, and then 3 minus x squared. So in this case, I'm thinking of the radius as being like a distance, as being a top minus bottom. So if you just want to plug in the formula and do it that way, you can. If you want to think about the radius as being a top minus bottom, like a 3 minus x, and then a 3 minus x squared for that red distance there, you can do that too. Because you're squaring these parts, it doesn't matter. So both of these will give you the same answer. Okay, so that's how we find volumes of rotation. As you would imagine, it's very similar if you're rotating around the y-axis. If you're going around the y-axis, your volume is pi times integral, a to b of f of y, or not around the y-axis, geez. Let's say you rotate around a line x equals k, which is of course a vertical line. So that'd be f of y minus k squared, and then g of y minus k squared. So that's how you would do that. So just to give a brief example like that, let's suppose we had like the function x equals 1, and then we have just the line across for a bound, let's say y equals 6, and then we have this curve in terms of x, it's x equals. So it's x equals square root y plus 1. And we're going to take this, and in this example, this is my area right here, and I'm going to rotate the pink area around the line x equals -2. So I'm going to sketch that in blue here. Again, that's my blue is for the axis. That's x equals -2. So we're going sideways. And if we're going sideways, that's an indication that it's going to be dy. It's going to be in terms of y. We're going perpendicular to the y-axis. We're rotating around that way. I'm getting circled. Obviously, it goes further over to the left. Okay, so what I'm going to do here is just use this formula. So furthest away from the axis, my outer curve is coming from the root y plus 1. My inner one is coming from just the x equals 1. Okay, so that means that my volume here is still going to be pi times. All right, so I have my outer radius squared. So I'm going around -2, so it's going to be root y plus 1 minus 2 squared. My inner curve is actually just the vertical line. The vertical line is just my inner curve, so that's just 1 minus 2 squared. Oh, 1 minus a minus 2 squared, that's my bad. And then my bounds, well, you can see in the problem, we're starting at y equals 0. We're going up to y equals 6. So that's the setup on that. Again, I have my outer radius squared, my inner radius squared. It's all going back to that donut shape and trying to work with that. Okay, I hope this helped. I hope the visuals helped. Thanks for watching. I'll see you guys soon.